So let's dive right in. Imagine this. You're an engineer, and you've poured weeks, maybe even months, into a new high-performance circuit. Everything should be perfect, but it's not. There's this hidden noise, this distortion you just can't seem to pin down. Well, today, we're going hunting for that noise. You've done everything by the book, right? You've got the best data converter money can buy, your power supply is squeaky clean, the clock is rock solid. And yet, when you run a frequency analysis, that FFT, your performance is just terrible. It's totally plagued by these unexpected harmonics and errors. So what's the ghost in the machine? I mean, this is one of the most frustrating problems in circuit design, but you know what? The answer is usually hiding in plain sight. Every good mystery needs a prime suspect. So, in our little investigation here, let's start by identifying the most likely culprit behind these performance-killing errors. And here it is, crosstalk. Yep, that unwanted guest at the party. Essentially, crosstalk is just what happens when signals don't stay in their own lanes. Whether it's through electric fields, magnetic fields, or shared connections, a signal from one part of your circuit just bleeds over and corrupts another. It's a super fundamental issue in pretty much everything, from audio systems to really complex integrated circuits. Okay, now this is the real kicker. This slide points out a massive misconception. We all tend to think of this kind of interference as just random noise, you know? Something that just raises the noise floor a bit. But that is not the whole story. The really crucial point here is that when digital signals crosstalk into an analog path, that error isn't random at all. It is a predictable, deterministic error that is directly dependent on the original signal itself. And that fact completely changes how we troubleshoot it. So we've identified our culprit, a signal-dependent error. Now it's time to move to the next phase of the investigation. We need to figure out its MO, its method of operation, by decoding its digital fingerprints. And this right here, this is our first clue. See that? A nice, clean, analog sine wave goes into our data converter. But look what comes out on the digital side, specifically from the most significant bit, or MSB. It's not a smote wave anymore, is it? It's a square wave, flipping between high and low. And here's the critical part. It's at the exact same frequency as our original input signal. So why does a square wave matter so much? Well, let's break down what it's made of, its frequency content. A mathematically perfect square wave is built from its fundamental frequency, which is our original signal's frequency, and then an infinite series of its odd harmonics. The third, the fifth, the seventh, and so on. This is the smoking gun, people. The digital representation itself contains the very harmonics we're desperately trying to get rid of. And is not just the most significant bit. Nope. Every single bit in that digital word is telling the same story. These patterns might look more complicated, but they all share one key characteristic. They are all just nonlinear versions of the original signal, and they repeat with the exact same period. What does that mean? It means they are all contributing energy only at the harmonic frequencies of that original signal. So here's where it all comes together. When the energy from these digital bits, which we now know is pure harmonic content, couples back into our sensitive analog path, well, we no longer have a clean sine wave. You can see it clear as day on this FFT plot. The corrupted signal now has these very distinct spurs right at the harmonic frequencies. See? This isn't random noise, it's harmonic distortion, and its fingerprints point directly back to our digital lines. Case closed. All right, we know the what and the why, but now let's get into the how. How are these digital signals actually escaping and finding their way into the analog domain? Let's take a look at the three main escape routes. Okay, let's break these down. First up, you've got power supply coupling. Your digital circuits are drawing these sharp, quick pulses of current. That causes the supply voltage to dip and bounce around, injecting that noise directly into any analog circuits that are sharing that same supply. Second, there's capacitive crosstalk. Just think, any two parallel traces on your board act like a tiny capacitor, coupling energy between them. And third, grounding. All those digital return currents have to go somewhere, and as they flow through the ground plane, they can cause the local ground voltage to bounce, creating errors for your super sensitive analog stuff. Okay, the investigation is pretty much complete. We know the culprit, we know its motive, and we know its methods. Now, it's time to fight back. Let's build your troubleshooting toolkit so you can prevent and mitigate this stuff in your own designs. And controlling these errors isn't just about playing defense. It's a whole field of precision engineering. I mean, check this out.
In high-end audio, for example, engineers don't just shield from crosstalk, they build active cancellation systems. They literally calculate exactly how signals will interfere and then generate an anti-crosstalk signal to cancel it out. It just goes to show you how predictable, and therefore correctable, these signal-dependent errors can be.
So, how do we block those escape routes we talked about? Here's your toolkit. To fight that capacitive crosstalk, physical separation is your #1 weapon. Keep those digital and analog traces far apart on your board. Shielded cables do the same thing for your wiring. To combat the grounding issues, you want to use things like ground loop isolators and balance connections, which are literally designed to reject this exact kind of interference. And to prevent that power supply coupling, use separate power supplies or at least dedicated regulators for your analog and digital sections. You got to keep their noise isolated from each other.
You know, in the end, it all comes down to this really powerful idea. Once you understand that digital crosstalk shows up as a signal-dependent error, not just as random noise, it totally transforms how you approach design and debugging. It shifts your focus from just trying to manage some vague noise to meticulously managing your signal paths. So the next time you see those unexpected harmonics, you won't just see noise, you'll see fingerprints, and you'll know exactly where to start hunting.